Thank you, Jeananne. So sort of cover all the bases and emphasize a few things that haven't been emphasized so far with bone, and especially I'm going to talk about the ratio of sodium to potassium. And thanks for hanging in there for a whole day to stay here. So here's my disclosures, and the one relevant to this talk is ILSI North America funded one unpublished study I'm going to tell you a little bit about. So some of the questions that I wanted to address in this talk and were asked to cover a little bit about mechanism, how do sodium and potassium affect heart and bone? Is the ratio more important, or at least equally as important as the individual nutrients? What's the strength of the evidence about that? How can recommendations be achieved? So getting around to the practical part, setting the DRIs and trying to translate it into an impact in the consumer. So maybe we'll get to, you got to increase potassium some and reduce sodium some, because either alone to try to do the whole thing is a pretty difficult challenge with American diet. Or North American diet, I should say. Should recommended intakes be tied to energy? So I'm going to come back to that theme that Larry started today and add my vote to how important that concept is. So first, to start a little bit about what sodium and potassium do at the cell level, and you heard a lot about renal function earlier. With potassium being the major intracellular cation and sodium being a major extracellular cation, the balance and the exchange between those two help regulate a lot of things. And for this discussion, most importantly, fluid balance and electrolyte regulation. And perhaps for bone health, the acid-base balance is relevant. So they share some pumps that coordinate tightly this interchange. So the role of salt affects heart and bone, and salt and its salt substitute, potassium chloride. We heard today some mention, is it the cation or anion? One of my favorite studies so far, I'll look forward to Bruce's China study, ultimately in the community. But so far, this study in Taiwan, where they went into VA institutions, and in half of them, they substituted out sodium chloride in cooking and on the table with half potassium chloride, and followed then coronary vascular disease mortality, and showed a 59% reduction over 5 years in those that had half of their salt substituted in this controlled environment where they were fed all the time. So that was pretty striking in 1,981 elderly men. Looking at the hazard ratio for the highest versus lowest quartile, now I'm moving into the ratio really quickly, sodium to potassium intake, both in the U.S. population and in Japanese, you see for several outcome indicators, all-cause mortalities or CVD or ischemic heart disease, an increase in hazard ratio with the highest compared to the lowest quartile of sodium to potassium. And this ratio is higher than either alone. You have to go to the papers to see the individuals, because I didn't cram on that many figures. So the little bit about the ILSI funded unpublished paper that's under review, we looked at NHANES data also in nearly 4,400 women and men over the period of 2011 to 2014. And we wanted to look at ratios, so not just sodium and potassium, but also magnesium and calcium and all the relative ratios from food and supplements to predict systolic and diastolic blood pressure and incidence of hypertension. So models were developed to do this. And one thing that my statistician, George McCabe, feels really strongly about is revealing the factors that contribute to the basic model, because if most papers you adjust for it and then it makes the diet look like a really big deal. But to put it in perspective, when you don't do that, age, race, or ethnicity explain 29% of the systolic blood pressure and 11% of diastolic blood pressure in women, compared to 15% of each in men. So that's the majority factors. Diet, any of the things we looked at, explained 1% or less of the variation. And I think that might be true of many other studies if they actually presented it this way. One of the things we are doing in this paper is looking at distribution of the population who achieve the ratios according to the recommended RDA and AIs. And the women are in pink and the men are in blue. Sorry for the stereotype. but you barely can see the people, the proportion that meet the ratio of sodium to potassium in either men or women. You barely can see the color because so few actually master that. It's because the sodium's way over the recommendations and the potassium is way under. So you have this result. We're just not there, not even close. It's a better for the sodium to calcium ratio because we're better off for calcium, even though it's a shortfall nutrient according to the Dietary Guidelines Advisory Committee as well. But so the sodium is the same as over here, but the calcium's better than the potassium. So now you can really see the pink and the blue, but it's still not even half. You'll have to go to the paper ultimately for all the other mineral ratios. And I couldn't actually present the visuals of the data because it's not published and this is going to be shared. But the sodium potassium intake predicted significantly systolic blood pressure in females and males, and neither of any of the minerals alone predicted significantly. So we found that the ratio was much more valuable. Molly and I will have to get together and compare these different approaches where we had a lot more subjects, but she had the advantage of 24-hour urinary sodium, and then we looked at different ratios, so we'll have to kind of compare notes. And we had a broader year span, whereas she used 2014, I think. Okay, there we go. Something that's published is on adolescents, looking at the ratio, showing as you increase sodium to potassium and look at blood pressure, you see this whopping increase in hypertension with ratios of sodium to potassium over 2.5. And so it's kind of at the extreme, but it shows that trend. Now to move to bone for a little while. If you're going to perturb anything about bone, you're going to affect calcium metabolism, because calcium is almost exclusively in the bone and it's there as a constant percent. So to follow the fate of calcium dictates whether bone mass is going to increase bone balance or bone balance is going to decrease. So I like to look at all the parts of the pathway of calcium metabolism to see where different nutrients affect it in order to predict what could happen to bone. And here you have sodium or salt and potassium right at the kidney affecting urinary loss. So ultimately it'll affect bone balance that way in opposite directions. So you have increased calcium coming out in the urine with increased salt and decreased potassium. And that's going to lead to more negative bone balance. Now you heard an elegant talk about what happens at the kidney. I'm going to do this picture in the context of what's happening to calcium by both sodium and potassium. So you have most of the calcium excretion through paracellular routes in the proximal convoluted tubule, 60 to 70%, and in the thick ascending limb, 25%. Both are very dependent on sodium and potassium. And then you have a bit over in the distal convoluted tubules that says transcellular route. on average, you lose 1 millimole of calcium, or 40 milligrams, for every 100 millimoles of sodium. Because they're sharing these transporters in the kidney, if you're excreting sodium to get rid of the extra sodium in the diet, you're going to lose the calcium out with it. So I want to take you to controlled feeding studies in adolescents that we have done at Purdue, where we varied the salt and looked at the influence on sodium balance and calcium balance. So these are in 3-week periods, and I want to bring up the fact that there's racial differences in sodium and calcium handling that influence ultimately blood pressure and osteoporosis. So they're crossover studies, 2-3-week periods where all the diet and beverages are controlled. So the basal diet is the same in both periods. The salt was varied in one period, and it was randomly assigned whether they were on the low or the high to start with. So 1.3 grams of sodium a day on the low and 4 grams a day on the high. And this was the best we could ascertain from the literature at the 5th and 95th percentile of sodium intake. So it was representative of something some adolescents consume, but at the extremes. And we varied this salt in the diet through Gatorade that we got that had no sodium in it, and we could add to it the powder, or soup. So several times throughout the day, they had the salt in this manner. Now, traditional theory is that you excrete all the extra sodium and you adapt within a day or 2 or 4 at the most, and then you get into this steady state. But we didn't exactly find that because there were these big racial differences. On the low sodium diet, the whites in yellow and the blacks in blue excreted the same amount of salt. But on the high salt diet, only the whites could excrete all that extra salt in the diet, and the blacks went to a huge positive sodium balance. Where did it go? Because it didn't influence weight, and we calculated by the physiology text that there should have been a 4 kilogram difference in 3 weeks with the difference between the amount of sodium that the blacks were retaining compared to the whites. I've looked up in the literature, and there's cadaver data showing black skeletons have higher sodium content than white skeletons. So my supposition is that while all of these bone nutrients were going into building peak bone mass, sodium's coming along with it. And it's at this period you can have this hidden amount of sodium in your skeleton, but a little bit older, when you're not acquiring that much bone, then it's going into increasing plasma volume and into hypertension. And so it's only this really critical short period where it might not affect blood pressure. There are methods being developed to find where that sodium's going now in soft tissues and bone, and hopefully we can address that at some point. So while the whites are excreting all that extra sodium compared to blacks, here's what's happening to the calcium. So the urinary calcium excretion is up really high in the whites that were putting out all that sodium, and blacks were holding on to the calcium because they're not excreting so much sodium. So that shows you there is an effect on calcium balance, which is the same as calcium accretion. From going from low to high salt, they both go down. But blacks, regardless of salt intake, have a much better calcium retention than whites. So even on high salt diets, blacks get away with it for bones compared to the whites. They're just so much more efficient at utilizing calcium and retaining bone, at least at this stage of life, which is an important one for building peak bone mass. So again, you saw one of these pictures from Larry Apple earlier. On that controlled diet for the solid 3 weeks, you had the girls bouncing all over the place with sodium excretion. The variance is just huge, even for 3 whole weeks. look at creatinine at the bottom to just contrast, because the creatinine is measured in the same samples as the sodium. And so this isn't about sample collection when they're in the same. This is about, there's a really innate different fluctuation of sodium connected to something that hopefully we'll figure out someday. And to look at the distribution of sodium excretion in these kids, there's a wide distribution all on exactly the same diet. And so 16% of them were misclassified on the high sodium intakes as being on low sodium diets. So you keep that in your mind in your epidemiology. Now I'm going to move to potassium in bone, and there's hardly any studies in this area. And this is one done by Selmayer's group out at University of California, San Francisco at the time, where she, for 6 months, gave elderly men and women a range of potassium intakes. They were assigned to 0, 50 or 90 millimoles potassium per day. Larry Apple and I were both co-authors of this study. She shipped all the samples to us to do balance. So the last week of the 6 months, they came into the clinic and they did a complete balance study. And so you can see how calcium balance improved on the bar graphs with increasing potassium diet. So very effective. Debbie thinks it's related to acid-base balance. So she measured net acid excretion, which went down. It is correlated. Whether that's direct cause and effect, I don't think we've determined for sure. We were hoping to do that study to set us up to do a randomized controlled trial with bone when this paper was published, and already did it. So what they did was potassium citrate, which is the same form that we used in our studies, compared to a placebo for 24 months. And it wasn't so much that potassium improved the bone mineral density, but it stopped the loss in the placebo group. So a significant effect of 1.6%. And there's your sum total of potassium randomized controlled trial in bone. I think we need to, so I'm appealing to the researchers in the room, the epidemiologists who have longitudinal cohorts. You could use this study that looked at sodium and calcium together as a model to go look at potassium and sodium. So over this longitudinal study for 2 years in Australia, Prince's group looked at, as you increase calcium, you have an increased bone mineral density change. As you increase sodium, you have a decrease. So he could predict then what could you do about manipulating calcium relative to salt to get at no bone loss. So he's saying you can either increase the calcium by 891 milligrams a day or have the sodium intake and accomplish the same thing. And see, we need that kind of equation for potassium and sodium. We don't know what the ideal ratio is. There is no currently accepted ratio, and that would be a really good thing for the committee to spend some time on. If you go by the AI of 2,300 milligrams of sodium to 4,700 milligrams of potassium, the ratio would be 0.49. If you look at the estimates of nutritional anthropologists of what pre-agriculture revolution estimate intakes would be, it'd be less than 0.3. But then came along processing of foods. We upped the potassium. We have not fortified with, or we upped the sodium. We have not fortified with potassium. So now our ratios are hugely varied around the world. For this intersalt study, the mean of 32 countries was 3.24, way higher than pre-agriculture revolution or the estimated or the recommended intake ratio. But look at the range from China at 7.5 to Yamamoto, Brazil, 0.01, just a huge range around the world. Some groups have recommended targets, WHO 1.0, the TOPE follow-up, a paper somewhere between 1 and 2. An interim goal might be 2 to get to for health, but can we achieve it on the American diet? Adam Dranowski did an analysis where he said, anytime you go above 1,800 calories a day, you've already exceeded the 1,500. Maybe you're going to slide it up a little bit. And to get to the potassium, you've got to be on 3,000 calories a day to get 4,700 on the usual American diet. So not very practical. We have to think about how can we achieve this balance of some sodium reduction, some potassium increase. When we look at what our children are eating, it's a pretty sad story. This is a fairly new paper looking at NHANES data in almost 10,000 kids aged 8 to 18 in the adults from NHANES 2003 to 2012, and they took 9 of the elements of the DASH diet. We like to attribute the DASH success to potassium and calcium and magnesium and whatnot, but it may be in combination with any of these other things: total fat, saturated fat, protein, cholesterol, fiber. We don't know how to weight those different factors. So what they did was say, what's the mean of each of these 9 factors on a scale of 0 to 9, 9 being best, and the mean for all of them were between 1.48 and 2.14. You can't do epidemiology on that when they're all clustered around the pathetic end. It's not distributed widely, so we're kind of stuck. So you've seen this concept from Larry about connecting it to energy. As he told you, sodium and calories have a correlation of 0.81, and sodium and energy has a correlation of 0.72. So it doesn't work practically to feed groups, feed families by these absolute cutoffs. So instead, think about a ratio of, or a target tied to calories of like 0.75 if you go by the lower salt level in the DASH diet. And then for different calories, that's what it would end up. So for one of them, you're at 1,500, and another one of them, you're maybe at 2,300. But we have tied B vitamins to calorie intake, and our recommendations can happen, or he suggests maybe a ratio. So I was asked to sort of summarize from my own point of view the strengths and weaknesses, and this slide's on cardiovascular outcome, and the next slide's going to be on bone. And despite what the AHRQ report says, it's about as strong a relationship as you can get of sodium to blood pressure in adults. I don't think any nutrient in any outcome measure could achieve the high rating if sodium can't. So I put it strong. It's dose response, generalizable for blood pressure. The ability to assess diet, as you've heard eloquently from Kay and others, is a weakness. Weak chronic disease outcomes beyond blood pressure, maybe it's going to get stronger. Children, moderate, there's kind of a lack of controlled feeding studies, which is the priority. I agree with Larry on that. And potassium, moderate, it's not as strong as sodium, but it's fairly robust. We don't have the dose response, and we don't have the diet trials we'd like compared to supplement trials. Children, it's probably not fair to say none. There's no good controlled feeding dose response studies. There's a couple of equivocal studies in the literature. And the ratio, although it's looking pretty good, there's just a lot fewer studies, a lot less look at it. Randomized controlled data are lacking only observational evidence. Now looking at bone, a lot weaker than heart. So there's some evidence in adults and children with biomarkers of a relationship of sodium intake to bone. No randomized controlled trials with strong disease measures. There's one dose response calcium balance study I showed you for potassium, and one randomized controlled trial in bone mineral density that I showed you. It's really scanty, and it's only in adults, essentially. And the sodium potassium ratio is just non-existent. I think a big problem you have to deal with is related to definitions. So the purpose of an RDA and EAR is to prevent deficiency. And here's quotes from the IOM. But you have, in the case of sodium, you're trying to limit it. not to get enough to conquer deficiency. That's not our worry at all. Is there evidence for sodium deficiency in normal acclimatized individuals in intakes below 1,500? Maybe you can wrestle with that. But just the definition of setting an EAR or RDA is a problem for a nutrient to limit. The purpose of the UL is to prevent toxicity. And here's the definitions from the IOM. If excess sodium intake is problematic and there's little evidence of deficiency in normal individuals, shouldn't we focus maybe on revising the UL or adding some clout to the UL? Research gaps. There's scant data in children using controlled feeding studies for heart or bone outcomes. For sodium, there's limited generalizability and dose response. From potassium, almost no data. It's not fair to say no data, almost no data. The sodium-potassium ratio requires a lot more study. It has a lot of promise. And we need to do things like fix one of them and then manipulate the other, because we don't know if it's the ratio or the absolute. And we need to attack that in a robust, rigorous way. Thank you.
Thank you, Dr. Weaver, for getting some of the bone story into this and the ratio a little bit more playtime. We're open for questions now. Any comments, questions?
I have a quick question. The slide that you couldn't show the data with just
Yeah.
the p-value.
I'll show you privately.
I see the p-value, but in keeping with what you had said 2 slides earlier, what % of the variation does the NAK ratio explain of the overall variation in systolic blood pressure?
Well, all of these things only about 1%, so it didn't exceed that.
Right. So even though it was
it's just significant
p-value, it's still
small.
a very small contributor.
Very small.
The study that was done on bone mineral density used potassium citrate.
Yes.
Is there a difference between potassium citrate and potassium chloride?
We don't know enough about bone, but it seems like the anion's really important for bone. But for heart, both of them have an effect. I've seen papers that say they're equal, the potassium chloride to potassium citrate for heart. And then there's one paper that I have with me, but I can't remember the authors, that suggests there may be some difference in the form, but it's potassium that works.
In your one of your initial slides where you had the data from Taiwan, and then you had another data set from the NHANES, and you compared the lowest and the highest quartiles. Did they control for all appropriate statistical or all appropriate covariates, or how did they do that? Do you know?
They did.
You know which ones, out of curiosity? Because that was a question we were talking about earlier, is what you control for.
I believe I brought that paper. Let me get it for you in a few minutes.
Okay,
yeah.
Thank you.
Any other questions, comments?
Yeah, actually, on that same topic on the second slide, where you're comparing the highest and lowest quartiles, and it's significant. Right?
So I didn't do that work. I was reporting it, and one was from Japan, and one column was from the U.S.
Right. So was there any evidence of a U-shape, like in the middle quartiles? Or maybe we should just...
I don't think they covered that.
Okay.
But I'm going to be fishing out that paper anyway,
All right.
so I'll leave it with the committee.
Thanks.
Go ahead.
This is a follow-up question to this same slide again. Just going back to what your statistician said about putting the unadjusted and the adjusted. It'd be very nice to see it for this paper as well, to see where you look at the ratio and how much of it's counted for by the two two extreme quartiles, and how many are how much variation is accounted for in the hazard ratio for the other variables.
So that wasn't my work, the U.S. and the Japanese.
Your work for your statisticians that said that.
Yeah. It would be nice to see it for that paper.
Statistician did the same thing. Look at it.
Okay, Connie, thank you very much.
You're welcome.